All right, today we are going to be reviewing topic 1 because you guys have your IFA next class. Whoop, whoop. I know you're as excited as I am. So hopefully you have all your notey notes that I gave you. You have your calculator handy and you have your books. I'm going to go ahead and use pages 41. Oh my gosh, 44, not 41, 44, 45, and 46 for the review. I may or may not do all of them. We shall see. I'm going to offer a very quick review of each of the topics, and then we're going to do the practice problems. And then hopefully that'll get you through your IFA. So first thing that we learned in lesson 1.1 was understanding irrational numbers. Through previous experience, my advice is just to remember what the irrational numbers are. Everything else then would become rational. So irrational numbers are non-terminating decimals, non-repeating, and imperfect squares. Technically, hold on, let me spell first. Imperfect, there we go. Woo. Okay. Technically, imperfect squares are going to be non-terminating, non-repeating decimals. These are decimals. Let's write that really quick. I don't want there to be any confusion. So if you tried to square a number, you're going to get a non-terminating, non-repeating decimal. But I like to say it because these are the only three things that are considered irrational. If it is not one of these three things, then it's automatically rational. And that is the easiest way to differentiate between rational and irrational numbers. In 7th grade, you had to fit them into these categories. In 8th grade, you were just talking about irrational numbers. Is it rational or is it irrational? So if you can remember these are irrational numbers, then you should be good to go. So keeping that in mind, let's look at, we want to know which ones are irrational. So we're looking for our 3. Are they non-terminating, meaning they never end, they don't repeat, and they're not perfect? That's what we want to know. So we're looking at 36. Now you should know in your brain 36 is a perfect square, but let's just say you don't for whatever reason. That's okay. You have your handy dandy calculator. Let's just clear it out just in case. 36. Oh, look at that. It's a perfect square. That is not irrational. That one would be considered rational. We have the square root of 23. Plug that sucker in there. Oh my gosh, that is not perfect. That is it looks like it terminates because there's not enough digits on my calculator screen for it to keep going, but it's not going to end and nothing repeats here. So it is definitely irrational. Let's take a look at this one. These ... means forever and ever. Not really. That's just what I say, but it works. So it's negative. We don't care because that's integers. Those could be rational. Does it repeat? We know it goes on forever. So the question is, does it repeat? 2, 3, 2, 3, 2, 3. Aha! It is repeating. So it's not non-repeating. It's rational. If they repeat, they go on forever. That is okay. They're still rational. Let's look at this one. This is 1, 5, 1, 5, 5, 1, 5, 5, 5. Ever and ever. Forever and ever. A lot of you guys are going to go, but it repeats. It's just 1s and 5s. I didn't say anything about a pattern. We could guess that this is going to be a 1, and then there's going to be 4 5s. But I didn't say anything about a pattern. It's not repeating. If it were repeating, it would be 1, 5, 1, 5, 1, 5, 1, 5, 1, 5. So this is not repeating. It goes on forever. So therefore, boom, you're irrational, boo. I don't care. 0.35, aha, bar notation. Bar notation means this 5 is going to go on forever and ever and ever and ever and ever, but it repeats. So because it repeats, it automatically gets to be rational. and pi. Pi is irrational. It is a decimal that does not repeat and goes on forever and ever and ever. You're irrational, my friend, and that's okay. So, if it doesn't repeat and it goes on forever and it's not a perfect square, it is irrational. That's the summary of the whole entire lesson. So would negative 0.25 repeating, that's what the bar means, bar notation, be rational or irrational? Explain. Absolutely, it is rational because repeating decimals are rational. Repeating decimals are rational. Let's write that down. Repeating decimals are rational. Okay? That was it. That was all a 1-1. So now, my friends, we move on to 1-2. If you forgot everything that I told you about 1-2, the most important thing to remember about 1-2 is if you are going to plot, compare, and order real numbers, I strongly suggest that you turn all of them into, we're gonna go Dora the Explorer. Decimals. Hey! You cannot, I repeat, you cannot compare numbers that are in different forms. The notes told you. I told you, some of you, when I came to visit you. You cannot compare and order them all mixed up like this. Please, 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 please make them all decimals. That's right. Even Sabrina Carpenter wants you to make them decimals. Okay? That won't help you on 1, but it will help you on number 2. So they're going to give you a bunch of all of this fun. Okay? Make them all decimals, and then you can plot them, you can order them, you can compare them. And I'll show you what that looks like at number 2. But first, we have some business to attend to in number 1. There are 2 ways that you can do this. There's the hard way, which I'll show you, and then there's the easy way. The hard way, which is not even that hard, is to say, is the square root of 89 a perfect square? No. But there are 2 perfect squares around it. What are they? Well, off the top of my head, I have 36, which is 6, 49, which is 7. The perfect square, 8 times 8 is 64. 9 times 9 is 81. This is 89, so I'm getting closer. 10 times 10 is 100. So somewhere between the square root of 81 and the square root of 100 would be 89, the square root of 89. So therefore it must be in between 9 and 10. Okay? The easy way, hey, handy dandy calculator. We're gonna put the square root of 89, and it's 9.4. So we know that it needs to fall between 9 and 10, because if you were looking at a number line, the 2 whole numbers that fall between, that 9.4 would be in between, would be 9 and 10. This one will be the small side, and then 10 would be the big side, and 9.4 would be closer to 9, but still in between them. Okay? For number 2, I'm going to turn them all into decimals. Yes, I am. Now this one is already a decimal for us. Oh, so I'm just going to go ahead and do 2.3333 because we don't know. We may need that later. So now we have to say, what is the square root of 8? 8 square root. Okay, I'm going to write it as 2.8284. Because you never know. You don't know how many you're going to need. we have 2.5, which is just that, 2.5. If you want to add some zeros here so everything makes sense, that's fine too. And then we have 2 and 1/4. I know 2 is going to go on this side of the decimal. And if you forgot how to make 1/4 into a decimal, divide the numerator by the denominator, and it's 0.25. So 25. And now we can order them using our place value. Well, all the 2's are the same, so that's fine. Let's go look at our 10th place. This is where we're going to get our order from. What is the biggest number we have here? So this one's going to be 8 is our biggest, so that's going to be our first one. Then we have 5, so that's going to be our second biggest. Then this one. Then we have this one. So it says to order them and locate them on a number line. So they all fall between which two whole numbers? I gotta work here a little bit. They fall in between the numbers 2 and 3. And then you have 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, 2.8, 2.9, and then 3. So I'm going to put 2.8 would be 1, 2, 3, 4, 5, 6, 7, 8, somewhere over here. That'd be the square root of 8. And then you have this one, 2.5. Well, that'd be 1, 2, 3, 4, 5, but that's just 2.5. So like that's easy. You don't have to do anything there. Then you have, wait a minute, I messed this up. This one's bigger, 2.3. Sorry, just kidding. There we go. Then 2.3, 1, 2, 3. That's this one. Repeating, and then 2 and 1/4. Sorry, here we go. Okay. If they told you to order them from greatest to least, this one would be the biggest. They said least to greatest. This one would be the smallest, and you would go that way. Make them into decimals. And also double check your work so you don't make a boo-boo like I did. But I fixed it, so we're good. 1-3. Square roots and cube roots. This one had a lot of different parts to it. Classify each number as a perfect square, a perfect cube, both or neither. So remember last lesson and in your notes, I told you guys to memorize your perfect cubes. If not, you can always just multiply up on your calculator. Perfect squares, you should know. If not, you can check those on your calculator, but calculators aren't really set up for cubes, to be honest. You just kind of gotta do the math. Really the highest number that I see here is 100. So you can do your perfect squares on the side of your assessment. If you create it, you can use it for the whole assessment. So let's pretend like this is our assessment. 1 times 1 times 1, we know is 1. 2 times 2 times 2 is going to give us 8. 3 times 3 times 3 is 27. 4 times 4 times 4, I think is 64, but let's double check it. We don't want to think. Haha. 5 times 5 times 5, I think is 125. Yeah. And I don't see any number bigger than that. So we're going to stop there for now. So we need to know, is it a perfect square, a perfect cube, both or neither? So we have 27. Let's check our calculator. Let's see if it's a perfect square, although we should know it's not. Ew, gross, no. But it's on our perfect cube chart, so we know this one is a perfect cube. And then it can't be both or neither. What about 100? Well, You should know it's a perfect square, but if not, that's okay. It is a perfect square. Is it on our perfect cube chart? Nope. So it's only a perfect square. 64. I kind of wrote through that one, sorry. Is it a perfect square? Spoiler alert, I gave you this answer another time. You should know that it is, but just in case. Hey, it's a perfect square. Is it on our perfect cube chart too? Oh, there it is. So this one is both. 24. We should know that it is not a perfect square, but we'll do it anyways. Ew, gross, no. Is it on our chart? Also no. Neither. A gift box is a cube and a volume. I warned you about these words. You see the word cube and they're giving you a volume of 64 inches. So what does that mean? You have to find if it's a cube and they gave you the volume, you have to find the cube root. What is each edge of the box equal to? What's the cube root of 64? Oh, magic. Oh, look, Sabine, this person has three cube shaped fish tanks. Tank A has a side length of 16, B 27, C 25, and we'll have to plot, order, and compare the side lengths. Ew, what do we have to do if we're comparing, and ordering them? Turn them into decimals. Yes. What is the square root of 16? 4. What is the cube root of 27? 3. What is the square root of 25? 5. So, B is the shortest side. They should have given us a little bit. C has the longest side. A is in the middle. I don't know. They should have given us a little bit more guidance. Just saying. All right, let's look at number 7 because I think this one threw you guys off. And we're almost done. I know this is a long one, but it's a whole unit. So like, worth it. Okay. For this one, I'm going to get out my green so we can kind of look at them as individual pieces. I think that this kind of threw some of you guys off because they added addition and multiplication and subtraction. But this is order of operations, believe it or not. And they tried to throw you off by throwing in some square roots and cube roots. So our order of operations say parentheses, exponents, and then multiplication, division, and then addition, subtraction. Because square roots and cube roots are part of the exponent category, you would actually handle those first prior to doing any multiplication, division, or addition, subtraction. And I don't know exactly if or when you were taught that, so shame on me for not making sure you were aware of that prior to today. But the square roots and cube roots fall into the E category of your PEMDAS. So you would actually handle those first and then do the other math. So keeping that in mind, let's look at this first chunk. Wherever you see that parentheses, that's, different expressions. So using our order of operations, the first thing we're going to want to do is take care of this square root here. All right. So we have 35.8 minus the square root of 121. If you don't know what that is, handy dandy calculator tells us it is 11. Now this is not 8th grade math. This is simple math. 35.8 minus 11, 24.8. And that's all you had to do there to figure that one out. Same thing for this middle piece, except now they're trying to give you a fraction and a square root to throw you off. We will not be afraid. We know what to do. We're going to handle our square root first. We're going to turn this into a decimal, and then we're going to do our addition. So the square root of 225 is 15. So we're going to write 15 plus, and we know it's going to be 10 point. And again, we're dividing the numerator 1 divided by the denominator 4.25. So it's 10.25. And now we have a simple addition problem. 15 plus 10.25, which gives us 25.25. And then in our third expression, we have 6.3 times the cube root of 64. Again, you can't use calculators really for cube roots, but we can use this because we made it. What is the cube root of 64? It is 4. So now we can go back to our calculator and say 6.3 times 4 equals 25.2. And now you can plot and compare these numbers based on the decimals that we got from those expressions. So this one would be the biggest because this is 2525. This would be considered 2520. This one's the smallest. If you were going to put them on a number line, this one would be closer to 24. This one would be closer to 26. I mean, you can now work with these numbers in decimal form. All right. Last thing was the last lesson. It was solving. Most important thing to remember is there are always two answers when you are squaring because you have a positive and a negative. Remember, negative times a negative gives you a positive. So, just saying, we can still use our cube root chart that we made on the other side. Just saying. And remember, if it's not a perfect cube or a perfect square, as long as you isolate, don't go crazy like her, you just leave the radical on the other side. So we've seen this one 100 times so far. How are we going to solve this? We're going to take the cube root of both sides. What is the cube root of 64? 4, because we saw it 100 times. How are we going to solve this one? We take the square root of both sides. And because it is a square root, we have two answers. It can be positive 7 or negative 7. Is there a cube root for 25? Let's go check our chart. I don't see 25 on here, so I'm not going to have a pretty answer. I'm just going to take the cube root of both sides and write it as x equals the cube root of 25. And is 125 a perfect square? I don't think so. I could be wrong though. Ooh, gross. No. So, square, it's a square. X equals the positive or negative square root of 125. Oh, We have a container, guys. It's a cube shape. They gave us the volume. It's 125. If they gave us the volume and it's cube shape, it has to be times 3x to the third power. How are we going to solve this? Take the cube root of both sides. These cancel. Is 125 on our paper? Look, there it is. So what does one side have to be? It has to be 5. Oh, we're geniuses. I'm very excited. I am hoping that with this review, you guys are now ready to take on that IFA. Kick butt, take names, make me proud. And don't forget, I readies. Woo! I ready, you ready, we ready.